Okay, piecing together some ideas on trigonometry for this chapter that we're in now. Chapter 5 is trig, and we want to rethink this stuff. I'm pretty sure this shouldn't be first intro to trig, so hopefully you've done some of this stuff before and want to take everything that you know about sine and cosine at this point and sort of reinterpret them and see how that fits in to unit circle trigonometry and the unit circle way of thinking about things. So trigonometry is, of course, named after measurements of triangles, and if you learned it from triangles, you should bring up what you know about that and reinterpret it in kind of a new setting here. We're going to do unit circle trig, which is going to lead into trig functions, which we have to think about. Graphs of trig functions is our primary focus. So the unit circle leads into that. Now, first of all, that means we're going to be looking at the unit circle. We're going to be thinking of our angles in radians instead of degrees. So I have this calculator. I went through the modes on here and made sure I changed this to radian mode. So it's interpreting all of my angles in radians. So when I do the sine of something, it's understood to be radians. But I want to kind of think about sine and cosine. The other trig functions are based on knowing sine and cosine really well. And knowing sine and cosine really well comes down to understanding the unit circle picture. The worst possible way to think about sine and cosine is that there are buttons on here that you can push and get results out of, right? It's a function, so you put in a number into it and you get a result out. But just pushing a button will get you the number, but that doesn't give you any kind of insight into what's happening. But I'm going to get some values down and we're going to think about them in terms of what they mean on this unit circle. So if I do stuff like sine of 2.5, I get a result out of it. So the sine of 2.5 is approximately 0.5985. So okay, that's a value. That's 2.5 radians. Since I put it in radian mode, it's thinking of that input as radians. And I'm just going to put some of these things down and then we're going to see what they really mean. Okay, so doing these calculations on here doesn't tell you much. Cosine of 4, I can do the cosine of 4, and that means 4 radians, or whatever that is, right? Cosine of 4, that one comes out negative 0.6536. These values are coming out between 1 and negative 1. And they always will. Cosine of 6 is positive 0.9601, but I'm just getting decimals between negative 1 and 1. And if you just have numerical results like that, doesn't give you a ton of insight right here. So we want to put those onto a unit circle picture. You do want to be able to do calculations on here and think back through things. And also what we will see is inverse sine and inverse cosine stuff on the calculator. Like if I'm thinking about 0.4 as an outcome, that would be a possible outcome right here. So if I want to answer this question, what do I put in there if I want to take the sine of it and get 0.4? This is not a one-to-one function, so there's a whole bunch of answers where sine of that would be 0.4. We'll see a bunch of them. But if we narrow down the domain enough into just like the fourth and first quadrant, then we have a one-to-one function, a narrowed down one-to-one function that does have an inverse. So we can think about the answer to this question being the inverse sine of 0.4. Recognizing that's only one of the answers that'll work in there, but we want to see that answer and then see how the other ones are related to it. It's all on that picture, on that unit circle picture when we get there. But we do have a way to calculate this. It's second sine or shift sine on most of the calculators. That's your inverse sine function. And I can put in, I put it in wrong, 0.4 as the input into that function, and the output will be in radians if I'm in radian mode. So that comes out 0.4115. That's radians. And that means that should work in there. So if I do the sine of 0.4115, that's one of the answers that'll give me basically 0.4 for the result. But what does that mean and what are the other answers? All takes place on the unit circle. So we'll get some work on a unit circle and look at that picture. Okay, now I want to get oriented with this picture here. This is what I call unit circle approximate, because I can get approximate values off from this just like I can on a calculator, what the unit circle values mean. So by unit circle, we mean all of the points that are 1 unit from the origin. So I have this kind of going around here, and you notice what the calculator is telling you in the upper corner here is that r is 1. This is theta, which is your angle in radians from the positive x-axis around. And these are the x and y coordinates of the actual point. Right, this is when x is negative 0.75 or so, y is 0.66. Those, as it turns out, are the trig values of this number of radians. So the x is the cosine of 2.417, and the y is the sine of 2.417. Okay, so the radians, we start with 0 here. The positive x-axis is our 0, and we measure the angle around from there. So that's starting from theta equals 0 and going around. I had these little tick marks on here to go. That's 0.5 and 1, 1.5 and 2, and so on. Halfway around a circle is going to be pi radians. It's 180 degrees or pi radians. And all the way around the circle is 2 pi radians. So that's 6.28 something. So 6 radians would be right here. That's where the measures are going to get used to. We're getting used to radians on there, and the trig functions just come from there. So those values that I did on the calculator have an interpretation now. If I want to think about the sine of 2.5, well, here's 1, 2, here's 2.5 radians. The sine of 2.5 is about 0.5985. There it is right there. So this is doing the sine and cosine as coordinates on here. The sine is the opposite side of a triangle. And if you picture a triangle right here, it's going to be a right triangle between the horizontal and vertical. And the opposite over the hypotenuse would be the y value over the r value. But the r value is just 1. So the sine is just the y value. And likewise, cosine is just the x. So here is a picture of the sine of 2.5 being 0.5985. The cosine of 4 was the value that I did before. Here's 3 radians, here's 4 radians. So the cosine of 4 does come out negative. You can see it up here as negative 0.653. It's right here on the picture. So what cosine does is go from any point on the unit circle. If you're doing the cosine of something between 0 and 2 pi, or even beyond that, it goes from a point on the unit circle to the x value. So it's an arrow from the circle to the x-axis. That x value right there is the cosine of this angle. So the cosine of 4 is negative 0.6 something. There's the actual x coordinate right there, but that's the value on the x-axis. The cosine of 6, well, we'd be almost around full circle then. So if I bring this around on the circle around to 6 radians, we're almost to 2 pi. So that's over here in this fourth quadrant. The cosine is almost to 1 again. We got the 0.9602. There's what that would actually round off to. That is the picture for what sine and cosine are doing for values between 0 and 2 pi here. And what the inverse, well, what the sine function does is just point to the y value on there. So sine is starting off at 0. Sine of 0 is 0, and it works its way up to 1 when we get up to, that's pi over 2 right there, and so on. So the sine of 2 would be 0.909 because we're still up here very close to the top. So the sine is just pointing to the y-axis. Now, if you go from a point on the circle to the y-axis, you just get one output to that. So that's a nice function. But if you're going from the y-axis out to the circle, if I start with a y value, like what happens when I just put in y equals 0.8, there's actually 2 different possible answers there. So if I'm starting with the output, the y value, I got 2 possible thetas that would go with it. So that's not a nice one-to-one function right there. I'm going to have to think of which one. That's not a function at all. 0.8 has 2 different outputs. But if I narrow this down to just the first and fourth quadrant, then 0.8 just has this first quadrant answer right there, and I want to think about what that is right there. What I just did was the inverse sine of 0.8. It's asking the question, what angle has a sine of 0.8, which is what angle on this unit circle has a y value of 0.8. It's going to be this theta right here, about 0.927. So that should be the inverse sine of 0.8, or the one that I did in the first part of the video was the inverse sine of 0.4. That's right here, 0.4 on the y-axis. So if I bring this down to where y is equal to 0.4, that's pretty close. We get about 0.41 radians. And that's the answer for inverse sine of 0.4. It's right in there somewhere. So about 0.41 something. So you could get approximate values right off from understanding this circle, even if you didn't have a calculator. If you had a well-marked unit circle, you can do sine and cosine and inverse sine and cosine right on here. That's going to take some getting used to, but that's what we're concentrating on, thinking of these functions in this way. The inverse sine goes from the y value out to the theta value on the circle, and the trig functions, sine and cosine, go from the circle to the x or the y-axis. X is cosine and y is sine. All right, different markings on this. It's still the unit circle. I zoomed in a little more, but I marked some particular points on here. And instead of thinking about when the theta values come out nice, which is not usually that useful, I'm thinking about some particular values where some interesting things happen on the circle. So these points that I've marked off here are the points halfway through each quadrant, in the sense that the angle is halfway through there, or we're just as far from the y and the x-axis. This is where x equals y, or x equals minus y over here. These are halfway in the middle of those quadrants. So angle-wise, if this is pi, this is 1/4 of the way there. So this is at pi over 4. And this is 3/4 of the way there, so that's 3 pi over 4. Those are halfway through the quadrant in the sense that the angle is halfway through. And we're going to see, of course, x and y come out the same right there. If I look at the coordinates of that point right there, x is equal to y, and you can work out the triangle there. These are both the square root of 2 over 2 for sine and cosine at that point, for sine and cosine at that point. Now, another kind of halfway through the quadrant is, what if you're halfway up? What if the value of sine of x is halfway up between 0 and 1? So sine of this is 0.5 right here. That ends up being 1/3 of the way through the quadrant angle-wise. So this is pi over 6. The whole quadrant was pi over 2. 1/3 of that is pi over 6. And that's where sine is 1/2. And the cosine value comes out. That ends up being the square root of 3 over 2 if you use Pythagorean theorem there. It's a triangle where the hypotenuse is 1 and this is 1/2. You find out that the third side has to be the square root of 3 over 2. That's this value. So that's what happens at pi over 6, or this is pi minus pi over 6, so 5 pi over 6. 6 pi over 6 is at the quadrant. 7 pi over 6 would be right here. You get those same kind of values. Y is negative 1/2 now, and x is negative square root of 3 over 2. But those 4 points marked off, kind of using the yellow and blue on here, are where the sine value is plus or minus 1/2, and the cosine is plus or minus square root of 3 over 2. Angle is pi over 6, or some multiple of that here. And these are just the other way around. This is when x is halfway through the quadrant. The angle is 2/3 of the way through there, or this is pi over 3, 2 pi over 3. Those are where x comes out exactly 1/2 or minus 1/2, and the y is the square root of 3 over 2. Those are the corresponding points in the different quadrants that go with those nice exact values. So you see what sine is doing is following a pattern from 0 to 1/2, square root of 2 over 2, square root of 3 over 2 up to 1, and then of course back down that same chain for the values over here, and then the opposites of them down here. So there's nice relationships there. We're going to get familiar with as we get used to this unit circle trig. I want to put some of those on paper and look at an interesting pattern there. It gives us some nice exact values. All right, back to the piece of paper now to make observations about the pattern that we're noticing there in the exact values. These are some useful reference points as you go through this thing where these values come out really nice. Now I'm going from 0 to pi, so we're really only doing first and second quadrant right here, and then it kind of repeats with the negatives. But theta starting at 0 and working its way up, we got 1/6, 1/4, 1/3 of pi up to pi over 2. That's straight up on the unit circle. And so now we're in the second quadrant coming back down. 2/3, 3/4, 5/6 is working its way back down until we hit pi over here. So I want you to see those on a picture. But the values are kind of interesting. What we noticed with those is the y value is working its way up to 1 and back down to 0. So it starts at 0, works its way up to 1, and then it's going to repeat those values coming back down to 0. But the interesting thing about the values in there is it goes up to a half. At these exact values that we want to mark off, this goes up to a half, square root of 2 over 2, square root of 3 over 2, and then it's coming back down through that pattern. But I want to kind of notice some things about that. Those are the values of sine right through there. But this pattern is kind of suggests an interesting pattern. And if you think this through, square root of 3 over 2, square root of 2 over 2, this is the same thing as the square root of 1 over 2, and this is the same thing as the square root of 0 over 2. So they kind of fit this nice pattern, 0, 1, 2, 3, and how about that? The square root of 4 over 2 is exactly 1. So the sine is equal to that pattern, going up from 0 to 1 by that little pattern, and then back down, square root of 1 over 2, square root of 0 over 2, back down to there. And you can do the second quadrant, you're just going to have negative values on that. And so those are easy to keep track of because they fit that nice little pattern. That gives us nice exact values to work with. And if you get that idea, it's not much different to do the cosine on there either, because cosine is just the x. It starts at 1, works its way down to 0, and then on down to negative 1. But it's going through those same values. So next to 1 is square root of 3 over 2, working its way down that same little pattern down to 0. And then we're going to go on down to negative 1 following the negative values. So they fit that nice, clever pattern. But as long as you know you're in the second quadrant, you know cosine has to be negative. So those values fit through there, and you should be able to keep track of the different values in there. It's not that much to memorize, and you know everything about those values. That gives you nice marking points, as we saw in the picture, right through those quadrants. And if you need one of those other trig functions, you can do that on here. If I needed the secant of 2 pi over 3, I'm just keeping track of the fact that secant is the reciprocal of cosine. That's the definition there. Secant is the reciprocal of cosine. So if I know the exact values for that, I can just do the reciprocal part. Reciprocal of negative 1/2 is negative 2, so that comes out great. Or if I need tangent of pi over 6, I just keep track of the fact that tangent is sine over cosine. That's a good way to think about your tangent function. One way to think of it. One thing that's true about it is it's equal to sine divided by cosine. It's y over x, or sine divided by cosine. So if you just fill in the values that you know here, that's 1/2. That's square root of 3 over 2. That simplifies nice. If you're into rationalizing the denominator, and you should be, square root of 3 over 3 is the exact value of that. So those are all based on just knowing these values, and that gives you nice angles to work with, nice outputs for your trig functions there. So those will be good exact values that will work a lot of our problems around those exact values.